Okay. Let's turn to another alternative of Durbin-Watson test, which is called Lagrange multiplier test. Okay, and this Lagrange multiplier test will release to avoid some of these restrictive features of the d-test. Okay, and the idea of this test, okay, you can see this one. Since Durbin-Watson test, it just limited to first order regression, serial correlations, and this one can be extended to the p-periods. So the idea for testing Lagrange multiplier test is using this regressions. Okay, and if, in other words, we're testing all this coefficient. If either one of them, at least one of them significant, means there's a serial correlations, right? Okay, so the hypothesis testing will be, alternative is there's no serial correlations, and alternative will be at least one of them is significant, right? Okay, so I'll show you the result from eViews as well as in the Grados. Okay, let's see the eViews. How did you get this Lagrange multiplier test? Okay, look at this one, view, and look at the residual diagnostics, and did you see that? Serial correlation, LM test. Did you see that? You all have that? Then it will ask you what is the lag, but in this examples, I'm going to show the different test with the same lag. So Lagrange multiplier test can also do for just first orders. Okay, so with this same orders, then we can compare the result, right? Okay, so here I'm typing 1. Okay, since I want to compare with the Durbin-Watson statistic. Okay, then I hit OK. Then, did you see that BG serial correlation LM test? Okay, this is by, did you familiar with this statistician? Burch Pagan. We learned that in chapter 10, right? BP, yeah, the same B, but this one is the other one. It's a B with another one, so I call it BG test. So it's BG-LM test, okay? And this BG-ML test means what? Means I add one more residuals, okay, in the regressions, okay? Then look at the top of these two statistics. Okay, this is one is F test, the other one is chi-square. Either one of them is okay. Okay, and the first one, F test. Look at the F test. We do have the numerator, degrees of freedom, and the denominator, degrees of freedom. Okay, so it is really tested this one. Okay, and so the F test, either F test or the other one is called chi-square test. What's the p-value? What's the p-value? The p-value. is pretty small, right? So that p-value compared with alpha means what? Those are p-value. You'll see that at the top. Those p-value means very smaller than alpha level. Means reject. The null hypothesis means reject. No zero correlation. And support zero correlation. Okay? And how about working with the grados? If we work with the grados, okay, I can also use the test and autocorrelation. Did you see that? So choose the autocorrelation. And I also use 1 since this is test the first order. So hit OK. So what do we have? The first one is the same as our F test. The second one is the same as our chi-square test. And they have another one, which is called, I even don't know how to pronounce these words, Elgin? I don't know how to pronounce this one. But this is called L-box, or just call them L-box. Q test. And this is another one. And then I'll show you that in eViews, you can have this one from eViews too. You'll have this page. You'll have this page. Do you? Can you do that from Python? Okay, sure. Do you? Steve, do you have that? Okay. All right, so the first two is really the same as what we have from eViews, right? And these two, we all call them Lagrange multiplier test. So there's two versions. Okay, one is using F test. The other one is using chi-square test. And how did you get the third one from eViews? Let's see. eViews, view. Residual. Yeah. Look at this eViews. Look at view. And did you see residual diagnostic? We just using test, right? Why don't we show the first one? Yeah, parallelogram Q statistic. And the lag is also 1. Okay. Did you see that? Since I have 1, so the lag is 1. And did you see that the autocorrelation? AC means autocorrelation function. Okay? There's a Q statistic, which is the one which is show you from the eViews. So let me show my eViews here. 7.94325. Did you see that numbers? And the probability is the same. Okay, so these 3 ways you can check with zero correlations. There's 3 ways to do it. Okay, one is Durbin-Watson, the other one is LM, and the Q test. And Durbin-Watson is really rigid to the first order, but LM test and the L-box test, Q test, is not only one first order. It's extends to P orders. An idea of this one, did you see the models? The dependent variable is all U hat, means the residual terms from the original output. Therefore, we need to have the original regression model and choose the test function in order to get all this result. So we do need to have the original model to check with whether we have the serial correlation problems in our original regression model. Dylan asked me this one 2 weeks ago. Last week he didn't hear. He's not here, right? Last week he's not here last week, right? Huh? He was here last week. Dylan? Yeah. Dylan asked me. He was here. Okay. Dylan asked me this output. Okay? And this is what we call serial correlations. So maybe, you can tell him that we learned it today. Yeah. When he asked me, then I told him that I'm going to cover this one next time. Okay? So if we have more lags, this is we need to type the lag, the periods of the lag, in order to have this output. If I have 10, then this output will have 10 autocorrelation functions, and each one of them do have the Q statistic. Okay? Right? So this 3 popular test is what we using to check with serial correlations. Any questions? Maybe get it from you do L box. How about the upper 2? Uncertain. Okay. I think the upper 2 is pretty popular in business school. But the third one is also popularly used in business school. But I really don't know about the engineering. Any questions? Any questions? From e-views or from
the
how do we check? Okay, this is what we call Q statistic, which is the same as this one, right? And did you see the probability? This is the Q test, the probability, this one. So is this one, this is to 5 decimal places, this is 3 decimal places. So they're the same. Just round it up, 0.005. P-value. 5%, then this is what? This is 0.005, and alpha is 0.05, which this is smaller than alpha. So reject the null hypothesis. Reject what? Reject no serial correlations. Null hypothesis is no serial correlations. Right? Alternative is serial correlations. the lag. In these examples, when I use the Durbin-Watson statistics, I'm using one lag, right? Because Durbin-Watson is just can check one lag. But this one can extend it to several lag. But I wanted to compare these two results. Therefore, when the computers ask me how many lags, I will just type one.
So the Durbin-Watson cannot do more than one lag.
No. No, they can only one period.
So for LM test, it can be more than one lag.
That's right. That's the difference. So LM test is more flexibility, right? Because all the serial correlation may not be limited to just one only, right?
If I change into
Two, okay, try it. Then you have this two lag. The first one is still is the same as one.
so what does it mean for the second one?
Means two lag. If I have two lag, means two lags. But actually, this is just only one lag. Maybe there's a two lag. Since it was two lag, this is still have zero correlation problems. So you can check with your EViews. If you put it two EViews, no, I'm sorry, Grados. If you put it Grados, yeah. Check no, the original output, yeah, test. What's the output? Yeah. This one, yeah. No. The original output. Where is the original output? Yeah, this one. So test. Do this one again. Autocorrelation. Yeah, if you put this two. Okay. This one is this numbers, which will be the same as what do you have here?
Yep.
Yeah, this one, right? So all this one is depends on how many lags did you insert in. So we will say that if we definitely know the lags, then it's easy to use this LM test. Sometimes you can use some other way to check the lags first, but I will teach that later on. Okay, now we just since we want to compare these two results and we already know the first order, so I'm using just one. Okay? You get it? Did you get it? Oh, you do. The first one or second one? Second and third one. Okay. Actually, the first one and second one is the same. We can check with using F distribution or chi-square distribution. Although the statistics number is different, but they're really the same thing. Okay. All right. So may I move on? Is that clear to all of you right now? So I'm through with how do we diagnose the serial correlation problems. Then the last issue will be any remedies. So do we have any remedies? Okay, this is what I have it. Remedies. So that will be our 9.5 remedies for serial correlation. But again, when we do, when we want to fix the problem of zero correlations, we need to make sure our model is specified correctly. Okay, otherwise we're working with some other problems, because the zero correlation problem can be caused by what? By model misspecification. When we say model misspecification, maybe omitted some important variables, or the functional form is different. Okay, so we want get rid of these two problems, and we're working with the pure zero correlations. Okay, so this is what we're saying, that if you conclude that you have pure zero correlation, then the appropriate response is to consider the application of general least squares methods, or we say Newey West standard arrows. There's two ways to do it. Okay, first of all, let's explain the generalized least square. So let's see the models. If usually it's pretty easy to using simple regression model to explain complicated question. Okay, so I'm always using the simple linear regression to do the explanation, that hope all of you to understand easier. So if we have first order zero correlations, so the model is like this one, and the first order zero correlations. Okay, look at this one, 918. Okay, if we have the model like 918, okay, and since this one is exactly the same as this one, so I can replace 918 to 919. Is any problem with these two equations? This is from our textbook too. Since this one is equal to this one, so I just replace that one into this one. Okay? Okay? Is that clear? Did that make sense? You know what I'm talking about, right? All right? And let's see. Since, since I have this ET from 918 and I have this row, then, and look at this 920. I use the lag. I put the lag, which from the 918 with the lag. So all the t becomes to t minus 1. So here I have 2t minus 1. And epsilon t is also t minus 1. And I also times rho in order to make this one t minus 1 with rho to eliminate this 2. Okay? So 918 becomes to 920. Then compare 919 and 920. Do we have the same of this one too? Right? Right? So I using 919 minus 920. So 919 minus 920. Left hand side minus left hand side. Right hand side minus right hand side. So I will eliminate this one with pure zero correlations. Okay, this is the purpose. Okay? All right? So it makes like this, 921. And since this is follow linear, classical linear model's assumption. Therefore, I can use OLS to do the regression OLS estimation of 921. And actually, my y variable turned out to be like this. I put the star signs. This is equal to this. And all the beta 0 star signs is this terms. Beta 1 is like this all terms in the UT. So 9.22 will be meet the requirements of classical linear model and do the OLS. And this is the generalized, the idea of generalized least squares methods. Okay? All right? And if this is so complicated for all of you, it really doesn't matter. You just say, I'm using generalized least squares. Okay? So you can do that from the EViews as well as from the Credos. Okay? I'm showing how to get the result from EViews. Okay? And actually, in the EViews, this is called general least square methods with Price-Winston methods. And Price-Winston methods, using our examples. Okay? Using our example, I'm really look at this one. This is the least square methods. And I'm using y. Then constant PC PBYD as the original model, right? Now I'm just getting another terms. I just type it AR1. Okay, means the first order serial correlations. Okay, then using the OLS, and it turned out to be the generalized least square methods. Okay? Okay? It's already done from the computers. Okay? So what I'm going to do, I'll show you. Oh, I'll delete it. This one, and I'll turn to our original one. Open as an equation. Okay? Now, from here, this is my original YPCPBYD, right? And I just type another one called AR1. Did you see that? I just add one more term called AR1. Okay? Then using the OLS methods, and do you see that? And this is the result. This is the result. And just look at this AR1. So after this is the remedies, right? So I put another terms called AR1, and then I fixed the original OLS estimation. And did you see these numbers? Did I just show the row? Did I just show the row here? This is what I say, Actually, I'm estimating this row. Okay? And this is row. And this is the result. So my output is like this. So I already fixed it, which is different from my original equations, right? So I'm going to name this one as equation 1. let me name the original one as an equation 2. Do I have the original one also? I don't have that anymore, right? So if I estimate using this is equation 2. I'll put this one 2. So I would have equation 1 and equation 2, right? Where's my and where did I get my okay, I have this one. Okay, I'll have this one, and where can I get my grados? Do I use the same? Let me see, where can I get my original one? The linear squares. Oh, I don't see that in the grados. Univariate time series. This one? Oh, generalized and AR1. Okay, then I use Y. Then, did you see that? Price, Winston. Did you see that? Then I choose Price, Winston. Then I hit OK. Did you see that row? Did you see that row? This one? Although I'll put it a little bit different, but compare with this one with views. Okay, look at this one. I think the coefficients are not exactly the same. It's different, but the row will be the same, right? Row. I'm sorry. Let me see. Did I have that? Where is my e-views? Where is my e-views output? Where's my e-views? I always have a hard time to go back to my original files. This one? Oh, this one? In the middle? Next, smaller? Yeah, I like to have my equation. Equation 2. Where is my equation 1? Okay, let me do it again, okay? Here, then just AR1. Make sure I have it. Okay, look at this two result. Name it equation 1, okay? All right, then using my grados. Look at this grados. And this is still a little bit different, but well, rho is pretty similar. Look at these two results. Okay? This one and this one. Although, it's a little bit different, but it's pretty similar. The result is pretty similar. It's a hard time for us to know how to those programmers, input all this, you're all programmers, right? How to insert the formulas in it. But this is slightly different. Y'all see that? Okay, so this is one method we call generalized least square methods, and this is the one which the lags. Since we're using lag 1, right? So you already know the lags. But most of the time, maybe we don't know the lags. There's another way, okay, to overcome the problems of generalized squares. Okay? Which is what? Which is called, this is Newey-West standard error. You all remember that in chapter 10, when we fix the problem of heteroscedasticity, we do have white correction standard errors, right? This is the same idea of that. Since if we have zero correlation problems, the coefficient is still unbiased. Therefore, we may just fix the standard error only. So the same idea is from heteroscedasticity. Okay? All right? So the EViews, we can use EViews to do that. Then how do we do that? Look at this one. Okay, let me do it again. Okay? Here, open as an equation. Okay? Before we don't fix anything here, but now we can do options. Choose the options. Then you'll remember last time we choose white. This time choose Newey-West. Okay? Newey-West. Then okay. So this is the Newey-West. So compare with the okay, I'll put this one as equation 3. Okay, compare this with my original. This is equation 2 is my original one. This 2 okay, this 2 do have the same coefficient, but different standard error. Do you see that? You all see that? Different standard error. And how about grados? Okay, how do we do with the grados? Model univariate time series. AR, then I hit general and lex 1. Let me see, 1. To 1. Let's see. Is that true? No, I didn't want to do this one. You see this one, and then this is not what I wanted. I'm sorry. Y. And PC, PBYD. Where do I get this one? Where is the time series? We can use the OLS. This one? And choose this one? Choose time series data. This one? And hit OK. Hey, where's my Y? I put a Y here. Okay? It works? So is this the same as what I have here? Where's my output? This one, right? HAC, this one? Let me have this one. Okay. Oh. Yeah, still they have a little bit difference. A little bit difference, right? Okay, this one coefficient is exactly the same, but the standard error is a little bit different. Okay? But the significance is the same. Yeah, I think the programmers, I don't understand. I'm not sure about those programmers. But actually, there's not, they didn't turn out a different result. That, for business students, this is good enough. But for this engineering students, maybe, you need to require more specific, right? For us, we just surrender, then say, oh, yes, we believe what you already have it. So this is two popular ways to fix the problems for serial correlations. Okay, so today I'm just talking about the problems of serial correlations. Okay, but there's a huge topic we need to cover, especially for time series. Okay, so next time, or maybe the following, today is April the 6th, right? And today is April 6th, right? Okay, so we do have exam week next week, then the 13th, then next time, we don't have a class next time. So I like to ask you, okay, whether you want to turn in the third assignment, okay, which is 9.7, lab number 5. Okay, you like to turn in next week and do the presentation the following week, or just turn in the following week, then do the presentation following week. It's you have choice. Which one you like to, what time do you like to turn in your assignments? Either next week or the following weeks. I mean, 13 or 20, you can choose one. Then I will just set up those assignment time for turning the third one, which is lab number 5, 9.7. And from this assignments, let's let's look at assignments, okay? And there's 7 steps. And for number 5, run the Lagrange multiplier serial correlation test. I'd like all of you to include the L box. I just introduced 3 ways, right? So step 4 will be Durbin-Watson test. The 5 will Lagrange multiplier test. We do have 2 Lagrange multiplier test result. So either, you can show both. But I like the third one is L box. Remember the one with autocorrelation function? Okay, include that in step 5. Or remember that? Step 5. Just say the question say run Lagrange multiplier serial correlation test. I like to include one more, which is called L box Q test. Okay? Okay, so when do you like to turn it? Next week or 13th or 20th. It's up, you have choice. But we don't have class next week. Okay? Okay, choose one. Presented on the 20th. On 20th, we don't have class next week. Exam week, we don't have no class on the exam week. But you are able, you can have the option to turn in next week or the 20th. Yeah, okay? Okay, that's that. So let's make it 20th, okay? So the third assignment is due 20th. Okay, I'll put on my assignment request. Okay? But remember the step 5, including L box Q test. Okay? All right? Any questions? All right. Then see you 2 weeks later. Okay, 20th, April 20th. All right. Thank you.